Good morning. So today we shall be discussing Heapsort, the last technique in the greedy method, that is the module 3. So what do we mean by a heap? A heap is a binary tree with keys assigned to its nodes provided the following two conditions are met. A very first condition says that it's a binary tree and it is essentially complete. That is, all its levels are full except possibly the last level, where only some rightmost leaves may be missing. And the second condition says that parental dominance has to be met. That is, the key at each node is greater than or equal to the keys at its children. So why do we make use of heaps? This data structure called heap is suitable for implementing priority queues. Priority queue is a set of items with an orderable characteristics called an item's priority with following operations that could be performed on it. Very firstly, we can find an item with the highest priority, and the second operation could be we can delete an item with an highest priority. Similarly, we can also add a new item to the set. And henceforth, heap is a data structure that can be used to perform sorting known as heap sort. So what does a heap look like? You can find some examples here. The very first tree that you observe here is a heap, as it satisfies both the conditions. That is, if you notice it's an essentially complete binary tree. All the left childs and the right childs exist except for a parent 7 which has a left child but doesn't have a right child. So we mean to say that this binary tree is having all the leaves or all the childs except for the rightmost leaf, which can be missing. And then the parental dominance requirement is also satisfied. So if you observe the non-leaf nodes, that is 5 is greater than its children, that is 4 and 2. Similarly, here if you observe the non-leaf node 7, which is a parent of the subtree which has only the left child, is also having a value greater than its child. And similarly, the root node of this heap, which has a value or a key 10, which says that it's also greater than its children 5 and 7. So therefore, it is an essentially complete binary tree as well as it satisfies the parental dominance. But whereas you observe the second graph, so wherein second type of tree, wherein you see that parental dominance is met. Parental dominance is met, but the subtree with 5 as its parent doesn't have a left child. So therefore, this is not going to satisfy the property of an essentially complete binary tree, and thus it's not a heap. So similarly, coming to the third example here, if you observe it's a essentially complete binary tree because it has all its left child as well as right child, and a subtree with parent as 7 is not having its right child. But things to observe is the left subtree whose parent is 5 has a child with a value 6 which is greater than its parent. So therefore, the parental dominance requirement is overruled. Therefore, this is also not to be considered as a heap. Thus, what we observe is the key values in a heap are ordered top down are ordered in a top down fashion. That is, a sequence of values on any path from root to leaf are in descending arranged in descending order. So if you see a path from 10 to leaf 3 says that it's a path which has values 10, 8, 5 and 3. So it is arranged in a decreasing fashion. So there are some important properties of a heap that we are supposed to be aware of. Very firstly, the height of an essentially complete binary tree with n nodes is equal to floor of log n to the base 2. That is, if you have an essentially complete binary tree with almost 5 nodes into it, then the height of this tree is equal to log n, that is log 5 to the base 2, which is nothing but equal to 2. Then the root of a heap is the largest element. So always to remember, the root of a heap is the largest element in the given list. So a heap is implemented as an array. A heap is implemented as an array by recording its elements in the top-down, left-to-right fashion. Heaps elements are stored in an array through positions 1 to n. So you can observe it here. Heaps elements are stored from position 1 to n. So as we have 10 elements into it, our first element is at the location 1 and the last element is at the location 10. We leave away the very first location, that is the index position 0, empty, because it can either be unused or you can put some large value, what we call it to be a zenital value. So parent node keys will always occupy the first n divided by 2 locations. So that is, if you can observe here, the parents in the heap are 10, 8, 7, 5 and 2, which occupy the first n divided by 2 positions, and the leaf nodes are occupying the last n divided by 2 positions. And if we say that 10 is at the index 1, then its left child is at the index 2i. So if I mean to say, if the value of the index j is equal to 1, the value of the index j is equal to 1, then I say that 10 is at the index j equal to 1. So its left child is at the index 2j. So it is at the index location 2. 8 is at the index location 2. Similarly, the right child of 10 is at the location 2j plus 1. So j's value is 1. Therefore, 2j plus 1 is nothing but 3. Thus, I say that its right child is positioned at the location 3. So, therefore, things to remember are the left child of any node at index j is always at index 2j, and the right child of a node at index j is always at the index 2j plus 1, and the parent of the node at index j is at the index floor of j divided by 2. So for example, let me say j is pointing to the key 8. Therefore, the value of j here would be the index of the element 8, that is 2. So who is the parent of 8? I can obtain it by j divided by 2. So j is 2 divided by 2 gives me a value 1. So it means that 8's parent is at the location 1. So at location 1 we have a value 10. There are two ways in which we can create heaps. One is the bottom-up heap construction mechanism and the other one is a top-down heap construction mechanism. So in case of bottom-up heap construction mechanism, we put everything in it, and then we try to fix the elements. But whereas in case of top-down heap construction, heaps can be constructed by successively inserting the elements into the empty heap. So first let us look into the bottom-up heap construction mechanism. Here we initialize the essentially complete binary tree with n nodes by placing keys in the order given and then heapify the tree. Starting with the last parental node, the algorithm checks whether the parental dominance holds for the key at this node. If it does not, the algorithm exchanges the node's key k with a larger key of its children. That is, if a child is greater than its parent, then we perform an exchange and checks whether the parental dominance holds for the key k in its new position. So this process continues until the parental dominance requirement for key k is satisfied. So after completing the heapification of the subtree rooted at the current parental node, the algorithm proceeds to do the same for the rest of the nodes or for the node's immediate predecessor. The algorithm then comes to a halt after this is done for the tree's root. So in short, we can say that step 0 is to initialize the structure with all the keys given in the order. And then starting with the last parental node, that is the rightmost parental node, fix the heap rooted at it. If it does not satisfy the heap condition, keep on exchanging it with its largest child until the heap condition holds. So we are going to repeat step 1 for its preceding parental node. So now let us have a look at an example here. We are given with a list having elements 2, 9, 7, 6, 5 and 8. So let us put them into a heap. So if the very first element is at the location 1, then 2 becomes a root. Its left child will be at the location 2 into I, so 2 into I, so I's value is 1. So 2 into 1 is 2, so therefore 9 will become its left child. Then 2I plus 1 gives me a value 3, so 7 becomes its right child. So 9 is at the location 1, 2, so therefore 9's left child will be at the location 2 into 2, that is at the index 4, and 5 will become the right child of 9 and 8 will become the left child of 7. That is, we consider the first element as root, the second element as its left child, third element as its right child, and the fourth element becomes the left child of 9, fifth element becomes the right child of 9, and the last element becomes the left child of 7. We always insert the parent, its right child, left child, and then move on to the subtree to put its left child and its right child. So now, if you observe, it's not a heap because parental dominance is still not met with. So we start with the last parental node that is rooted at the node 7, parental node rooted at 7. It does not satisfy the heap condition, so therefore we exchange the value of this root with its child. So therefore 8 becomes the root of this subtree. 7 comes to the place of 8. Similarly, moving on to the left subtree here, we observe that the parent node 9 is greater than its left and right child. So then, if you observe here, the subtree rooted at node 2 has a left child with value 9 and has a right child with value 8. So again, heap condition is not satisfied. So what we do is, the largest among these two children is going to replace the value of root. So therefore 2 comes to the place of 9. 2 comes to the place of 9 and 9 becomes the root of the heap. And then still, if you observe this subtree here, 2 is the root having children 6 and 5, which is again not satisfying the parental dominance. So therefore we shall again heapify, that is, we replace the value of this root by the value of the largest child. So therefore 6 becomes the root of this subtree. 2 comes to the place of 6, and then if you observe, this subtree is satisfying the parental dominance condition. This subtree is also satisfying the parental dominance condition, and similarly this subtree is also satisfying the parental dominance condition. So therefore we have already heapified the array. So this is how we construct a heap by making use of a bottom-up approach. So now let us look into its algorithm. So given an array, we are supposed to convert it into a heap. So given an array, we are supposed to convert it into a heap. So what we do is, we start from the last non-leaf node. So if you remember, the parental nodes begin, or parental nodes occupy the place from, occupy the first n divided by 2 locations. So we start from the last parental down, parental node, until we reach the root. So we try to heapify the sub trees rooted at I. So k is assigned the initial value of I, where the subtree is going to start from I, and you are trying to fix the element v into its proper location, into the heap. So v has an element at the location h of k. Initially we set heap is equal to false, assuming that it is not satisfying both the condition, that is, it's not satisfying the property of the heap structure as well as the parental dominance property. While it's not a heap, and 2k is less than or equal to n. So we already know 2j is giving us the position of the left child. So it means that if 2k is within the array boundaries, then there is a left child in the tree. So if 2k is less than or equal to n, then it means that there still is a left child. So what we do is, so now j is going to point to the left child. J is going to point to the left child. Then if we are going to check to see if there exists a right child, such that the right child is greater than the left child. If that is the case, Then we try to increment the value of j by 1. Thus, j is now pointing to the largest key amongst the children. Now we check to see that we are trying to shift that we are shifting an key that is larger than the child. If that is the case, we set heap to be true. Otherwise, we pull the largest child into kth position and j will now become a new k. And we do it as long as the heap property is satisfied or k is already a leaf node So at the end of the for loop, the subtree starting at I is converted into a heap. We do it till I becomes equal to 1, that is, we have reached the root. Therefore, the whole binary tree now is converted into a heap. So how efficient is this algorithm in worst case? The height of a heap is said to be h is equal to log n to the base 2. It was the very first property that we had seen about the heaps. Thus, in worst case, each key to be inserted will have to travel to the leaf level h. Therefore, moving to the next level down requires two comparisons. One to find the largest child and the other one to determine whether exchange is required. So therefore, the total number of key comparisons involving key on the level I will now require 2h minus I number of comparisons. So therefore, total number of key comparisons in the worst case are equal to summation from I to h minus 1, summation of all the keys in all the levels of the tree into 2 into h minus I, which after mathematical induction reduces to theta of n. The other method of constructing a heap is by making use of a top-down heap construction technique. So top-down heap construction is an alternative to construct the heap. Here we insert a new node with key into a heap after the last leaf of the existing heap and then shift the key up to its appropriate place as follows. Very firstly, we compare the key with its parent's key. If the latter is greater than or equal to the current key, then stop. Otherwise, swap these two keys and compare the newly inserted key with its parent. This swapping continues until the newly inserted key is not greater than its last parent or it reaches the node. So let us see an example. Here we are supposed to construct a heap for the array which has elements 2, 5, 3, 1 and 8 in it using a top-down approach. So very firstly, the first element 2 is now considered to be the root of the heap. The next element 5 is the left child of the heap, but we see that this subtree is not satisfying the parental dominance, so we shift 5 into its root location as 5 is greater than 2, and after it we insert the next element 3 as the right child of the heap. So if we observe, the children 2 and 3 are lesser than the parent 5, so therefore parental dominance condition is met. So the next value 1 is inserted as the left child of the left subtree whose parent is 2. So 1 is lesser than its parent 2, so therefore the heap condition is met, parental condition is met. So the next element 8 is inserted as the right child of the parent 2. So here 8 is greater than the parent 2, so therefore we again heapify, that is we move 8 into the root of the subtree and 2 comes to the position of 8. And again to observe, now this subtree rooted at 5 says that it is not satisfying the parental dominance condition. So therefore the largest among the two children, that is 8, is now shifted as the root of the tree and 5 occupies the previous location of 8. So this is how the top-down approach works. So now let us have a look at heap sort technique, a sorting mechanism. So it's a two-stage algorithm that works as follows. In the first stage, we construct the heap from a given array, and in the next step, we try to perform maximum deletions. That is, apply the root deletion operations n-1 times to the remaining heap. As a result, the array elements will be eliminated in decreasing order. So what is the root deletion algorithm say? So root deletion, the root of a heap can be deleted and heap is to be fixed by following these steps. Very firstly, replace the root with the key in the last leaf and then compare the new root with each of its children. If one of them is larger than the root, exchange it with the largest of these two children and continue this comparison or exchange with its current children until it reaches a level of a tree where it is larger than both its children. So let us see how it works with the help of an example here. So we are given with a list with an array with elements 2, 9, 7, 6, 5 and 8. Let us first construct a heap. So if you observe, we have constructed a heap by following the bottom-up approach, or you can also follow the top-down approach. And then the second stage, that is the root elimination. So for the first time, what we do is we shall exchange the last leaf's value with the root. So now the last leaf's value is 7, the root's value is 9. So 9 comes into the place of 7, 7 goes into the place of 9. 7 goes into the place of 9, and then let us say we delete the last node which has 9 in it. So we now place 9 into the sorted subarray. So 7 has become a root, so therefore 7 is in the first location. So now let us check if placing 7 in the root, is it going to satisfy the parental dominance? If I place 7 in the root here, then its left child has a value 6, but whereas its right child has a value 8. So therefore its right child is greater than the value 7 that is at root. So again we perform heapification. So 8 moves to the root and 7 comes to the right side. So now this node has already been deleted. This node is already been deleted and 7 is coming. 7 is at this location and 8 is at the root of the tree. So now what we do is we again push the largest element to the leaf. So 8 comes here. So 8 comes here and 7 becomes the root. So this leaf node is also deleted. So 8 also now enters into the sorted subarray. And then the root of this heap has a value 7. Its right child is 6. Its left child is 6. 6's left child is 2 and right child is 5. So heap is satisfying both the conditions. So now the largest element 7 will now be moved onto the leaf which has a value 5 and 5 goes into the root of the heap. Correct? So then 7 is deleted from the heap. So 7 enters into the list of sorted subarray and then 5 occupies the place of 7. And this process continues until all the elements in the heap are sorted. The time efficiency of heap sort is considered to be theta of n log n. Therefore, the array elements are eliminated in the decreasing order. So today we have seen what do we mean by heaps, and we have seen the two mechanisms of heap constructions, that is the bottom up and top down construction mechanism, and we have seen the heap sort technique. Thank you.